G'day, in this video, again, we're continuing to look at two-dimensional problems, but this time we're going to start incorporating frames of reference into our solutions. So here we're going to be looking at dot points 1.2.4 and 5, applying all of the basics that we have learned around motion in a plane and applying them to scenarios with different sets of frames of reference. And that's what these sets of dot points are describing. Here we're using the idea of being able to analyze and use vectors and applying that to the concept of frames of reference. And here in this dot point number 5, we're being asked to look at specific examples and apply all of these concepts and understanding to those specific situations. So for example, a boat on a flowing river relative to the bank. That's actually quite similar to the paddleboard question we did last video. There's also two moving cars, as well as an aeroplane in a crosswind relative to the ground. So today, our learning intentions is to apply concepts of relative motion that we've already learned about, just put them into some two-dimensional scenarios. In this video, I'm not going to be covering any specific practice questions. Instead, what I'm going to be doing is looking at set scenarios and trying to show you how to resolve multiple vectors and bring in the frames of reference concept. We'll then do some practice questions following up in the next lesson. So first off, and this is the main concept covered in these dot points, is looking at how to calculate relative motion between two moving objects. So already we know that if we're trying to calculate relative velocity of, say, A to B or B to A, we need to subtract the velocity of the observed object from the velocity of the object which is doing the observing. So for A relative to B, what that means is if B is the observer and it's looking at A, we take the velocity of A and subtract by B. If we're looking at B relative to A, where A is the observer, we take the velocity of B, the observed object, and subtract the velocity of A, which is the observing object. However, we're going to apply some of our vector analysis concepts to these because obviously we need to be using diagrams and vectors because we're working with two-dimensional motion. And here we're going to take that subtraction and turn it into an addition of a negative value, just like we've been doing in the last few sets of lessons and activities. So for example, VAB, so A relative to B, we're going to take VA and instead add negative VB, or in other words, flipping vector B and adding that on instead. Same thing for the velocity of B relative to A. We're going to have velocity B and add on the flip version of velocity A. Let's just do a quick example to visualize what I'm talking about. So let's say we have object A moving in an upwards direction and object B moving towards the right. If we wanted to draw the vector for velocity of A relative to B, what we would need to do is take vector A and add the negative of vector B, which would be vector B in the opposite direction. When we do that using our head to tail method, we should end up with something that looks a little like this. If we're looking to draw the vector for velocity of B relative to A, it'd be really similar, but we would take B first and add the inverse vector of A. When we combine those together, we should end up with something looking like this. Also keep in mind that VAB and VBA are always going to be the inverse of each other, and that's something that we can begin to see and appreciate diagrammatically. We have VAB going in a roughly northwest direction and VBA going in a roughly southwest direction. So the bearings should be essentially a 180 flip on each other, and the size of that vector should also be the same. Hopefully we can appreciate that just simply by thinking about our Pythagoras concept. So effectively in the previous slide, I've just demonstrated that this concept can be applied to any set of two-dimensional problems. Specifically, if we're making some syllabus links, the two moving cars example in dot point 5 is where we start looking at examining the relative velocities of two moving objects. So in an example, when we have car A and car B, I'll just draw a different set of velocities here. So let's say car A is moving in a westerly direction and car B is moving in a southerly direction. The velocity of A relative to B can be found as the velocity of A plus the negative velocity of B. Demonstrating that as a geometric representation, I'm going to take my velocity A And I'm going to add on the negative version of velocity b. And the resultant then would look something like this. And that would be the velocity of A relative to B. The next question could be, well, what if the observer was stationary? It wasn't one of the moving objects. Essentially, this applies to the boat on a flowing river relative to the bank and the aeroplane in a crosswind relative to the ground examples. We're going to look at the boat example to begin with first. So to do that, we're going to sort of just draw out a diagram of the scenario, and that's going to require us to have a bank on either side and a river in the middle. So I quickly draw that stuff out first. Now, part of my drawing, but we'll attempt to draw some sort of simple boat. And that is moving in the river. We also have an observer observing from the bank, and that's going to be our observing frame of reference. And essentially, you're looking at the motion of a boat. So if a boat is flowing on a river, there might be two different motion components that are involved. So for this example, let's say that the boat is moving from the right bank towards the left bank and is doing so at 3 meters per second. However, if the river is flowing, so this might be our current here, at 4 meters per second, the person on the bank is not just going to see the boat moving from one bank to the other, nor is it going to see the boat just moving down the river. The person is going to observe a combination of the two. So really, this question is actually quite simple. All we need to do is put together a little bit of a vector addition. So we're going to take our first vector here, as well as our second vector, 3 and 4. The resultant vector is simply going to be an addition of the two. And that is going to be the velocity that the person on the bank observes the boat going in. Essentially, it's going to be moving along the river and to the other end of the river at the same time. So some sort of diagonal going this way roughly. We can then just go through all of our normal analysis techniques to figure out what the bearing is, as well as what the combined velocity of the two components are. Now, the second example about the aeroplane is actually really similar to the first. I guess the biggest difference is that the height of the observer, who is going to be on the ground, maybe jumping apparently in this situation, we'll put them on a little box maybe. The person that's on the ground observing is at a different height to the plane which is flying through the air. But in this example, we are not going to be considering the motion of the aeroplane going in an up and down direction, only forwards, backwards, and side to side. And that will require us to think about the plane moving from, say, a top view. So the plane itself will be moving forwards, obviously, through the air. But this question also shows that there might be a bit of a crosswind at play. So let's say the plane is moving at 300 meters per second, and that the crosswind is blowing the plane towards the left at 15 meters per second. Similar to the first example, all we would need to do is some simple vector addition to then draw out our resultant. And that's going to be a combination of the two vectors, be pointing us in the right direction of where the plane is actually traveling through the air. And from here, we can calculate a bearing as well as a magnitude of the total velocity of the aeroplane. Now, yeah, these questions are pretty straightforward. We'll go through some of them in class and just practice to make sure that we get the basic concept. And that brings us to the end of Module 1. Congratulations, this is the first module of 8, the first of 4 for the Year 11 component of the course. In the next series of videos that you'll be looking at, we'll be tackling some concepts that come up in Module 2, which is all about dynamics. So already in Module 1, we've been focusing on being able to measure and describe motion. However, in Module 2, our focus is going to be on how motion comes to be, what causes it, and how motion can change. So yeah, I'll see you in the next set of videos for Module 2.